Hi, today we will continue to deal with the rotational topics because so far we have seen rather some elementary part of it. First, in the first two lectures on rotational dynamics, we have seen first the basic quantities corresponding to the linear motion, for example, linear velocity and angular velocity, linear distance x and angular displacement, which is the angle theta, linear acceleration if there is a change in the velocity, and angular acceleration if there is a change in the angular velocity. This kind of correspondences were seen and some problems were solved. In the second part, we have seen another important idea, which is the rotational moment of inertia, the quantity that corresponds to the mass in linear motion, because in the angular motion, the thing that corresponds to mass in linear motion is the moment of inertia, or rotational inertia, I. M times r squared, and with a constant in between at the beginning. So it is always some mass multiplied by some distance squared, but also a multiplier in front of it, maybe 1/2, maybe 2/5, maybe 2/3, etc. So we have seen those moments of inertia, and also the rotational kinetic energy, because if we have some object, a car moving, for instance on a road, it has a kinetic energy which is 1/2 mv squared. It is obvious, and we have already seen it in the previous chapters. But if something is rotating in the same place around the fixed axis, for example, such a wheel as we have shown before, if it is turning around the same axis without any movement horizontally or vertically, just this motion is an angular motion around the fixed axis. So this object should have an energy, a kinetic energy, and that rotational kinetic energy was last time calculated to be 1/2 I omega squared, because 1/2 mv squared in the linear motion corresponds to 1/2 I omega squared, etc. But today, in the third and last part of rotational dynamics, we will start to see first the torque, concept of torque, and then also the rolling motion, and another very important thing, which is the angular momentum. So today we also have a lot of work to do. Let's start with the concept of torque. What is the meaning? Maybe most of us have an idea in mind what a torque could be. For example, when you read the booklets of some cars, for instance, it says it has a torque of so much, for example. But what is the meaning of a torque? Whenever we hear the word torque, we should first of all consider some rotation, and some force is applied to a rotatable object, maybe an axis, a cylinder, or a disc, etc. But it has, in fact, maybe two definitions. One is a vector product, cross product, that we have seen in chapter 1 at the beginning of the term, of course, and the other is I times alpha. So we will first see the vector nature. For instance, the definition of torque, first one, let's say, is R cross F. It's a cross product. Torque. The torque is defined by some cross product. So torque is a vector, therefore we use a vector product. It is the product of R and F. But what do we mean by this R and by that F? First of all, we should maybe mention the corresponding quantity, because in the previous chapter, at the beginning of the rotational dynamics, we said that some quantities are corresponding to each other. So in linear motion and in angular motion, we had some objects. Let me have a short review on these. For instance, x, the linear distance in a motion along a line, is generally written by x, and it is in terms of meters. So the corresponding thing is, remember, angle theta. And also think about the units, because x is in terms of meters, angle is in terms of not degrees, as I said before several times. Angle is in terms of radians. Initial velocity in a certain interval, final velocity at the end of that interval, v0 and v in the linear case, maybe horizontal, maybe vertical, maybe at a certain in a certain direction, etc. So these things are omega 0 and omega, as we have seen several times and solved examples on it. Time is, of course, still the time t, since we are moving at, objects are moving at non-relativistic speeds. Non-relativistic means they are very, very much lower than the speed of light. So the everyday objects, the things that we are dealing with in Physics 101 are even the rockets, if there is any rocket, planes, airplanes, etc., are much, much slower than the speed of light, so that we have non-relativistic speeds, and therefore time concept is the same. Whether we are moving on a line or we are rotating around an axis. So time is still time t. However, if the objects were moving at some maybe half of the speed of light, or 1/3 of the speed of light, for example, at such extremely high velocities, then the time intervals also will be a bit modified. Time length contraction, time dilation times would seem to be a bit longer than the times in the non-relativistic case, etc. But this is outside the scope of Physics 101. So times are the same. And the other important thing is the acceleration, linear acceleration A, angular acceleration alpha. Also, after these kinematical parameters, we have other things, which is, let's say, mass m in linear motion. Now this becomes inertia I, that we have seen in the previous rotational dynamics 2. Now we are today in the rotational dynamics 3, third part. Also, now this is the new thing, I will write, which is the concept of force in the linear case, because you apply a force to lift up an object, for instance, or you have a weight that is exerted on you by the gravitational pull of the earth, etc. So this is the force in terms of newtons, that mass in terms of kilograms, inertia in terms of kilogram meter squared, as we remember. Also these are meters per second, and these are omega radians per second, and the times are second and second. Times are, of course, second and second. Linear acceleration meters per second squared. This is radians per second squared. Now what about the force? F is written, if numbers are given, if it's not a parametric problem, the units are, the unit of F is, of course, Newton. And we have a torque. This is like the shape of a hammer, for instance. So that letter, this is not T. It is a, this thing is letter tau in Greek alphabet. So this is the torque tau. And what about the unit? We have force times distance, so we should have Newton and meter, as we will see. And there is one more thing, which is the linear momentum and angular momentum. I will talk about it later when we see the angular momentum in this part of the lecture. Alright, so tau is defined by some cross product. It's a cross or vector product. We have seen these vector cross products in chapter 1. Since the result of this product, multiplication, is a vector, we call it vector product. It is also called cross. It is also called cross product because there is a cross between the two terms to be multiplied. And since the result is a vector, it is also called vector product. But the same thing. Okay. Since R and F are vectors, they have directions. But when do we use the concept of torque, for example? When we, let's say, open or close a door, open or close a window. First of all, please think about it for these applications. Let us open a door or close it. Let us, without any calculation, let us open a door. So let me draw a XYZ system and a door so this is the door. There is a knob here and this is the axis. So if we apply a force to it, but your force should be at right angles to this axis, and that is the radius r from the axis, because it can rotate around the z-axis. If you open it, for example, now it becomes, let's say, now you are applying a force to it, and this is the radius from the axis of rotation, x, y, z axis. This is the axis of rotation. So the door can be opened or closed, turned around the z axis. So r is the radius vector. R is a vector. Don't forget to use this arrow to show that it's a vector. R is the radius vector. But it is not the radius of a circle. Please don't expect to find a circle whenever you see the word radius. It is the radius of this motion. Because when you try to open this door, which is initially closed in the xz plane, now you turn it around the z-axis, so that this is the force you apply, you exert on the door to open it, and this is the knob, the handle, the knob of the door, so you pull it by applying a force on the knob, and it turns around the z-axis so that this is the radius vector, perpendicular, and your f is, let's say, perpendicular. Your f doesn't have to be perpendicular as we will see, but assume it is perpendicular, so they are at right angles. So we have two vectors. Let me show them by these pens. For example, r is the radius vector for the knob, the point where you hold it. And black one is your force F, so that they are at right angles, and this black one tries to open it. But we consider only the beginning, because after that the angle between them may change. After you continue, maybe you simply pull the door towards you, so that as the door starts to open, that angle now becomes more than 90 degrees, more than pi/2. But assume at the beginning they are perpendicular, so that R and F are two vectors. In this case they are perpendicular, but in general they don't have to be. So the result is a vector torque. But since it is a vector multiplication, we should have a direction because the result is a vector. How do you find the direction of the vector at the end of this multiplication? By the right-hand rule, as we have seen in chapter. Maybe some of us have forgotten the application of the right-hand rule. Let's remember it. When we have two vectors R and F, or A and B, U and B, two vectors which are multiplied by this cross product, then the resultant vector, direction of the resultant vector can be found by the right-hand rule. You first, let's say, look at the vectors R and F. So R is, let's say, this one, and F is the other one. Maybe you can put them in this order. So first one, the order is important, as you remember maybe. Order is important. So R cross F and F cross R are opposite vectors, not the same. So R cross F, R and then F. So one finishes, the other starts, R and F. If you follow this line, this path from the beginning to the end by your right hand fingers, then your right hand thumb shows you the direction which is perpendicular to this plane. So thumb shows you that torque is in the z-axis. So torque is in the z direction. If these are x and y, acting in x and y axis, then torque is in the z axis. You can also look at it the other way. For instance, R and F can be put like this. Not one end comes to the tip of the other, but maybe the two ends may correspond like this. But the order is from the first to the second, from R to F, from red to black. R to F, again, your right hand thumb necessarily defines the direction which is perpendicular to this plane. But F cross R, if it were the reverse order, F cross R, then first you would curl your right hand fingers from the first to the second, F cross R, and your thumb would show just the opposite sense, which is the negative z-axis. So R cross F and F cross R are two opposite vectors. So please be careful about the order, first of all. R cross F, or U cross V, V cross U, as we will see in the examples. Now let's consider some examples how to take the cross product of two vectors. In chapter 1 we had seen if we are given two vectors, U and V for instance, how we take their cross product. For example, if vector U is given as, let's say, A times I plus B times J and C times K. A, B, C are numbers, for instance, in general, as you will see. And the other one, V, let's say D, E, and F, where these are, let me repeat, where A, B, C, D, E, F are just numbers. Maybe some of them are zero, are just numbers. If U and V are given by these, then the vector product U cross V can be found. Of course, there are maybe two ways. One is the sort of longer way, but the other is more practical, as I will show you the shorter one. U cross V can be found by a simple 3 by 3 matrix. Can be found by, let's say, a 3 by 3 matrix. And at the top, let me write just the unit vectors I, J, K. And since first we have to write U, the components of V, and then the components of V, we write A, B, C, the coefficients in the middle line. So these are simply A, B, C. And then the components of the second vector, which is vector D, such as D, E, F, will come in the bottom line. So we have D, E, F. Therefore, A, B, C, D, E, F, this is the order. And then what do we do? We will take the determinant of this 3 by 3 matrix. Determinant is the following. We will simply, let us write the determinant of this 3 by 3 matrix. So we start with that determinant of this. Determinant is, we start with vector I, vector j, and vector k multiplied by. When you take I, start with the first one, I, you closely row and column and row of I. Okay, so please try not to see that. So this column of I and row of I are closed. And what are we left with? B, C, E, F. So that we multiply B and F and C and E. So that I times B times F minus C times E. B times F minus C times E. Whatever number there is. Similarly, we have, now we finished this. Now we are interested in the middle one, J. But in front of I and K there is a plus sign, in front of J there is a minus sign. That one comes from, as I will say here, from the sign convention. So in the middle one, again we follow the same procedure. We close the column and row of J. So that we see only A, F, C, D. A times F minus C times D. A times F minus C times D. And here, this is also finished. In the last case, we have the unit vector K, so plus. In the last case, we do the same thing, of course. We close the column and row of K. So we see only these four. A times E, so the product is A times E minus B times D. A times E minus B times D. So this is the end. Whatever numbers we have, we will just put them and get a numerical result. So many I's plus so many J's and so many K's. Why do we have a minus sign here? Is the following. Because of the following reason. For I, we have number of rows and columns, such as 1 and 1. I is here. It's first column, first row. 1 plus 1. So it is number 2. Number 2 is an even number. So that minus 1 to the power of 2. K. What is the row and column of K? Third column but first row. 1 plus 3. 1 plus 3 is 4. 4 is an even number. So that minus 1 to 4. But for J is in the second row, column but first row. So it is 2 plus 1 or 1 plus 2. 1 plus 2 means 3. 3 is an odd number. So that minus 1 to the number 3 is the following. Therefore, minus 1 to even power is plus 1. Minus 1 to even power is also plus 1, plus 1, plus 1. But minus 1 to odd power is minus 1. So that we have plus and plus for I and K, but minus for J. That is the reason. Alright, otherwise we are interested basically in the products of these terms. So let me now apply a numerical case and see the result. For instance, if u is equal to 2i plus 3j minus 4k, and the other vector v is minus I plus 4j plus 2k, what is u cross v? Is a simple application, just based on this idea. So it is easily found. U cross V is, we prepare a 3 by 3 matrix. I, J, K are the vectors, unit vectors. And as we have seen a minute ago, we will put these coefficients of the first one, U, which are 2, 3, minus 4 in the first row, 2, 3 and minus 4, but then the components of the second, which is those of V. Minus 1, be careful with the signs, please. Minus 1, 4 and 2. Let's see what we get by applying this idea. So that U cross V. Now we start with unit vector I. So if you close the column and row of that, we have 3 times 2 minus these. 3 times 2 minus 4 and minus 4. Middle line. Now you close the column and row of j, so we have 2 times 2 minus the others, minus j, 2 times 2 minus 1 and 4, minus 1 and minus 4, and finally k. This time you close the column and row of k, so you have 2 times 4 minus 3 times minus 1. So 2 times 4 minus 1 times 3. So we will see what we get at the end. Let's start with the first one. I times 6 minus 6 plus 16. 6 plus 16 for the first component. Don't forget this minus, please. Minus j. 4 minus another 4, so they cancel. So as we see, there is no j component. Plus k. 8 minus 3, 8 plus 3. So the result will be, therefore, U cross V turns out to be 22I plus 11K. There is no J component. If there were some, for instance, if this were 5 minus 4, we would have minus J as well. What do we get if one component is missing, for instance? So let's do the second case. Let me call A, for instance, and B is a simpler one. If, for instance, one component is missing, so we only have U is equal to 2I plus 3J. If U is equal to 2I plus 3J and V is equal to let's say minus I, no J, but plus 2K, for instance, plus 2K. If you were given these two new vectors, which have one term missing, having only two components, but be careful which one is missing. So then, U cross V will be what? In this case, we will have the missing terms 0. I, j, and k. First one has first component 2, second one 3, but there is no third one. 2, 3, 0. 2, 3, and 0. But the second one has one term missing, but that missing one is the j. So minus 1, 0, plus 2. Minus 1, 0, and plus 2. Then I times. If you close these, you get 6 only. 6 minus 0. Minus j. You close this one. So 2 times 2 minus 0. 2 times 2 minus 0. And k. You close these and then 0 minus 0 minus 3 times minus 1. So the result will be u cross v now 6i minus 4j and plus 3k. Okay? So although both of them have one term missing, the result consists of 3 terms. It is possible. Because maybe you can find the reason. Because not the same terms are missing. In the first one, k is missing. In the second one, j is missing, the middle one. So that, and then we can have the resultant vector cross product having all 3 components. Alright. Now we have seen this much in chapter 1. This is just a short review. Now we will use it in the talk. That's why we had seen the vector product, the rules of vector product. And don't forget also that, please note that. Please note that u cross v is minus v cross u. So if you change the order of these two terms, vu, then you necessarily should have a minus 1 in front of one of them, so that they point in opposite senses. They are opposite vectors necessarily. U cross v and v cross u are opposite, because as I said before, using the right hand rule, in the first one, if this is u and this is v, u cross v points in the plus z axis, but v cross u points in the negative z axis. That's why they are opposite vectors. For example, let's consider a three-dimensional frame, XYZ system, again. And for instance, again we are trying to open a door, for instance. And this is the radius vector from the z-axis. And this is your force, and they are perpendicular. In that case, let's say if r is equal to 2 meters, it's a relatively wider door, for instance, 2 meters. Of course, if r is 2 meters means magnitude of r is 2. Otherwise, how can you show this vector r if length of r is 2 meters? But vector r, if r is 2 meters and F is equal to, let's say, 10 newtons. So this is just the length and that is just the magnitude. And how if r and F are these, what is tau? Torque vector tau. So it is again easy to calculate, but you should first consider them in the related directions. So r vector, how do you write r vector? this is the magnitude, but since this is the x-axis and r points in the x-axis, so it should have unit vector I. So vector I is 2 times I meters. And F similarly, F points in the y direction, so that, and F is 10, but J, 10J newtons. So that tau, which is R cross F, can be easily found by the right hand rule. Also, it can be checked by the matrix notation. Let's first try to find it visually, so that using the right hand rule, from R to F, of course, tau should point in the z direction, and the magnitude should be the product of 2 and 10, 20k. We expect tau is equal to 20, 2 times 10, 2 times 10 k, which is 20k Newton meter. But we expected using the right hand rule. Can we check it by the matrix notation? Of course we can. Also, tau is I j k for the 3 by 3 matrix. And what are the components of the first one are? There's a 2 for the first one too, but there's no j component, no k z component, so that these are 0 and 0. What about the force? Force has a y component but no x or z, so that 0, 10, 0, 0, 10 and 0. So it is easy to get the result. Tau will be I minus j and plus k. If you close the column and row of this, you get 0 times 0 minus 0 times. There is no I component, obviously. 0 minus 0. If you do it to the middle one, j, you close the column of j, row of j, again you have 2 times 0 minus 0 times 0. 2 times 0 minus 0 times. There is no contribution from the first one and the second one. But the third one does have a component, because if you close the k, then you have 2 times 10 minus 0. 2 times 10 minus 0. So these are nothing, therefore tau turns out to be 20k Newton meter is the unit. So that's the case for this. But F and R may make an angle other than 90. Okay? For example, but in general, R and F may make an angle theta other than 90 degrees, other than pi over 2, maybe 40 degrees, 10 degrees, minus 110 degrees, depending on the case. And in that case, what do we have? If they make an angle other than 90 degrees, for example, we don't draw it like this, but maybe at a different angle, F. But this angle between them, let's say theta is, let's say, other than 90 degrees, other than pi over 2, maybe larger, maybe smaller. Okay, that means F has 2 components. One along the, then F, it means this one and that one. F sub x, F sub y. Okay, then F has 2 components, and in the multiplication, in the matrix operations, it has 2 components. So the result will be something different. But for the cross product, one interesting thing is this. For any cross product, for a cross product, let's say U cross V, we have 0. Of course, if one of them is 0, obviously you get result 0. If there's no force, of course there's no possibility of talking about the torque. Also, if there's no R means the following. You try to, let me draw it here. This is the door in the XZ plane. So this is the door. Let's say it's a glass door, for instance. But if you apply a force on this z-axis, you apply your force on this z-axis, which means there is no R. Or if you try to apply this somewhere here, your force is applied to a smaller R. Then, in the case of application on the z-axis, there is no R, so obviously there is no torque. But this is a possibility, 0, if one of them is U is 0 or V is 0. But there is another possibility for that. It is also 0 if R and V, U and V, if U and V are parallel. They are parallel or antiparallel. What is the difference between these two? For example, these two vectors, U and V, are parallel, and then they are pointing in the same direction and in the same sense, because each direction has two senses, one this way, the other opposite way. So this is the case of parallel vector. That is the case of antiparallel vectors. So for example, this combination is parallel combination, but that combination is antiparallel combination. In the case of parallel combination, we have angle 0. And since sine, as we see, sine of the angle is the multiplier, sine 0 is 0. But in the case of antiparallel one, theta is equal to 180 degrees between them. So this is the angle. Again, sine 180 is also 0. So in these two cases, we have no vector product, although both are non-zero numbers vectors. So one possibility for being 0 is that one of them is 0. For instance, no application applied force, or no distance between the axis and your force. So it is directly applied to the axis. So if you want to open this door, you don't try to open it by applying a force to the axis of rotation. You try to pull it by some distance. And the easiest one to make the torque as high as possible is to use the knob. Okay? Is to use the knob. Because otherwise, if you apply a force to such a distance, it means you have some difficulty. Unnecessary difficulty. Because although you have the possibility of applying at a greater distance, you choose a smaller radius. So your force, some of your force is lost, unfortunately. So you try to pull it or push it just with the greatest possible R value, which is the knob, so that they put the knobs, handles, as far away from the axes as possible on the doors and windows. If you put a knob just at the middle, then you have some difficulty in opening it or closing it, because you don't use the full R efficiently. So if you have just a knob here, for instance, let me show it here. So this is the possibility. And let's say you apply your force here or there, or there. So in these cases, you have, let's say, R, and this is also R, and this is also R. In the case of first one, for instance, F1, F2, F3. So torque 1 is just, let me say, forces are the same. So the magnitudes are F1 equals F2 equals F3. Let's say all of them are 20 newtons, whatever. But the distances, the radius from the axis is different. 1R, 2R, 3R. In the case of torque 1, torque 2, torque 3, so we have only 1R times F, F1, let's say they are all F. R times F. In the case of the second application, since the distance is 2R, 2R times F. In the third one, 3R times F. So obviously, torque 3 is greater than torque 2 is greater than torque 1. Although the forces are equal, because of the different radius of application, torques are not the same. And what is the easiest way of opening this door? Maybe it's a very, very heavy door, maybe. The entrance door, which is quite heavy for a massive object. Then you first choose the greatest distance from the axis of rotation, and second thing is you choose the perpendicular direction, because also torque is R times F times the magnitude of torque is magnitude of R and F times sine theta. By definition, in the cross product, the magnitude of the resultant vector, that of torque, tau, is the product of R and F. Let me use a simpler notation without the absolute value signs. So torque is R times F times sine theta. So R should be as large as possible, so that they put the knobs on the farthest away position from the axis of rotation, and you try to hold it. Your force has a certain maximum, it is up to you. You cannot make it anything larger, so this is your force. But you apply as high force as possible. But the other important thing is the angle, which is more critical than the others, because if you apply the angle, let's see the top view, let's look at the door from above. So what do you see? Top view is the following. So this is the y direction, x direction. This is the y direction, that is the x direction, and this is the door. Okay? This is the door. So this door is, so you see the top surface of the door. And the possibility, this is the knob. The handle is here, so this is the handle which corresponds to this one, and that is the origin, this is the origin, alright? And that's the x-axis. So you have several possibilities for applying direction, angle. So for instance, let's say this is the perpendicular direction, but you may apply your force at such an angle, or at such an angle, maybe this way, but the other one is, let's say, along the y direction. Which one do we choose? Normally, of course, intuitively, without any knowledge of cross product, okay, anyone without any physics notion even applies his or her force at right angles to have more efficient application. That's the reason of sine theta. Because if you choose an angle, what is the angle, by the way? Radius RF. So this is the angle theta. If the angle theta is, let's say, 40 degrees, 50, 60, whatever degrees, less than 90, you have some torque, which is not still, it didn't attain yet the maximum value. But this is the maximum possibility of the torque, because angle is 90 degrees. Sine 90 is the greatest value of sines, which is 1. But if you exceed the right angle, 100 degrees, 120 degrees, whatever, until 180. Again, this is getting less and less. Your torque is getting less. Although you apply the same force at the same radius, because of the change of the angle, your torque is decreasing. When you come to the angle of 180 degrees, such as these parallel case or anti-parallel case, and then you have no possibility of applying any torque, because sine 0 is 0, sine 180 is also 0. That's why there is no possibility of rotating any object by applying a force just along the radius vector, r vector. You should at least have at least 1 degree between them, so that may be difficult, but you can get some rotation, some torque. Otherwise, it is impossible to rotate the object by applying two vectors just in the same sense or in opposite senses. So please keep in mind this last definition, the magnitude. It is a cross product, yes, and it is found by this matrix matrix operation by the determinant of that matrix. However, the magnitude is, if you know the magnitudes of R and F, you should also multiply by the sine of the angle between them. And that angle shouldn't be 0, shouldn't be 180, at least. These are, and what is the maximum case? What is the easiest possibility? Of course, it is the 90-degree case where R and F are perpendicular. So far, that's why I've been talking about the 90-degree angle, because that corresponds to the easiest one, the greatest cross product. Now let us see a combination of forces applied to a certain axis, for instance. Let's have in an example, let's find the torques of some forces applied at different positions at different angles. Let's say this is the fixed point A, and this is the top view. To the rod, to the massless rod, let's forget about the mass, to the massless uniform rod of length B, whose top view is seen some forces are exerted. Some forces are exerted as shown. Exerted at different points and different angles as shown. And at different angles as shown. Find the resultant torque on the rod. For example, let's apply a few forces. Let me divide it into 4 equal pieces first of all. Each piece corresponds to B over 4. So each one, let me show just one of them. This one is, for instance, B over 4. each piece corresponds to 1/4 of the rod. Second thing is, so let's show some forces F1 at right angles, F2 at an angle, let me call it theta. This one F3, but there's no angle. And F4, this is the angle phi, for instance. So find the resultant torque. Alright, first of all, in this case, there are two possibilities for the direction of torque. Either clockwise or counterclockwise rotation. So which one of these forces we'll try to turn it, because that's the fixed point. So the rod can rotate around the rod can rotate around the point O. So this is the fixed point. So the rod can rotate freely if forces are convenient. If there's a net force, net torque at the end, resultant torque, it can rotate around point O. We know this. So, for instance, what are the forces that try to rotate it clockwise, in the clockwise sense? F1 will try to move it just by F1 without seeing others. Just focus on this one. If there is no other force but only F1, then this F1 will try to rotate it clockwise. F2 will try to rotate it counterclockwise. F3 can have no rotation because it is in the same axis as the rod. F4 will try to rotate it clockwise. So F1 and F4 try to rotate it clockwise in the sense of the hour clock, but F1 and F4. F2 in the counterclockwise sense, F2 counterclockwise. And F3, no rotation. Because the angle between R and F3 is just 0, so that sine 0 is 0. Alright, so this is the grouping. Two of them in the same team, the other one is the opposite team, the opponent, and fourth one will have no effect on rotation. So that torque is tau 1 plus tau 4 minus tau 3, first of all. And then, what are the torques, each of them? Tau 1, it is the distance, half of it b over 2, tau 1, half of it b over 2. Multiplied by the, let me write the definition for 1 once. Tau is equal to r times f times sine theta for each torque. For each force, therefore for each torque. So that tau 1 is just distance for F1 is half of the rod b over 2. What is the force F1? What is the angle? They are at right angle, sine 90. Sine 90. So this is just 1, so that tau 1 is simply bf1 over 2. bf1 over 2. What is tau 2? Tau 2 is trying to rotate counterclockwise. However, what are the distance and angle? Distance is 3/4, 3 over 4b, 3 over 4b, multiplied by f2, but don't forget the angle. Angle is not 90. Angle is, in this case, it is not theta. What is it? It is the other angle, R and F. This should be the angle, which is 180 pi minus theta. So sine of this is simply corresponding to the sine of that. F2 and sine pi minus theta. And what is that angle? What is that sine? It is sine theta again. Because if you separate F2 into components, if you have some difficulty in such angles, you may use the other way. What is the other way of thinking? F2, for instance, can be thought as composed of two components. So this F2, for instance, this F2 is what? It has a x component and a y component, and that angle is theta. So that Fx does nothing. Fx, F2x is already in the sense of just like F3, so it doesn't have any contribution. But the opposite one has some contribution, and opposite one is found by the sine theta. So this is also sine theta. Tau 2 is simply 3 over 4 bf2 and sine theta. And don't forget that it is trying to rotate it in the counterclockwise sense. Next we have tau 3, F3. F3 has no rotation obviously. Tau 3 is, distance is b, length is F3, but there is no angle sine 0, so there is no contribution. Tau 3 is simply 0. And tau 4 is, F4 is here. But it is at a distance of b over 4. 1/4 of the full length of the rod. Force is now F4, but what about the angle? The angle between them is just a very large angle. However, you can simplify that by again separating F4 into components, horizontal and vertical. This F4, let me show just F4 here, for instance. This F4 can be thought of having two components. One like this, one backward. This one doesn't have any effect because they are R and Fx are antiparallel vectors. So, however, this one does an effect. It does have an effect, so that it is sine opposite side, so sine phi. So this one is F4 sine phi. Therefore, this corresponds to b over 4 F4 sine phi. So totally, this is the other one. Totally, we should add first and fourth and subtract third from them. Totally, tau is equal to, just the magnitude, 2, 1, bf1 over 2, bf1 over 2. Tau 4, which is this thing, plus b over 4, f4 sine phi, and minus tau 3, which is, tau 2, tau 2, yes, this is the second one. That one will be subtracted, the other is already 0, obvious. So this one is negative now, negative 3 over 4 bf2, bf2 sine theta. So this is the final result. Of course, you can simplify it by taking b and b over 2 outside. You can have some simplification, but this is the main idea. I hope everyone has understood how we find the torques if several forces are applied to a certain object at different positions, at different angles. First of all, you should determine which of them try to rotate the object clockwise and which of them try to rotate it counterclockwise, and group them in these two parts, and also decide which one has no effect. The parallel ones, the antiparallel ones will have no effect. So this is the main idea. Now let's consider the some circular objects, such as a disc, a wheel. How do we write those forces? If a rope is passing over a disc, for instance, then as you see in the following examples, if this is a disc, and let's say we have maybe some object is hung here and some of them is there. Let's say this is F1, for instance. Tension T1, tension T2. For example, if you try to pull these ropes, the wheel is fixed, the disc is fixed, the pulley, so it can rotate around this fixed center. But different torques, different tensions are applied to the two parts, let's say, so that, and T2 is greater, for example. T2 is, let's say, this tension on the right hand part is greater than the tension on the other side, for example. But that is the radius R. And as you see, they are at right angles, so that torque is, since T2 will try to rotate it clockwise, but T1 will try to rotate it counterclockwise, we have to subtract the torques. Since they are applied at the same radius, so it is R times T2 minus R times T1. So yeah, you can write this R times T2 minus T1. Please don't confuse torque and tension. This is T, that is tau. Greek letter tau. But if, for example, we have two discs having different radii, but juxtaposed, attached to each other. For example, if this is the bigger one and that's the smaller one, so the side view is, let's say, like this, for instance. If this is the case, for example, so that distance is, let me call it R1, and that one is called, let's say, R2. So this radius is R1, and that radius is R2, for example. And this is the top view of this couple of these two cylinders attached on top of each other, for example. And assume that now tensions are, maybe T1 is applied here and T2 there. In that case, of course, unlike the first one, radii are different. So that T2 again will try to rotate it clockwise, T1 counterclockwise, but you multiply them by different radii. One with R1, one with R2. Let's use the same numbers, indices are the same. So that torque will be subtraction of them, just like the subtraction of these, but not R and R, but R1 and R2. So clockwise sense, it is R2 times T2. R2 times T2 minus R1 times T1 minus R1 times T1. So please try to see the difference. If they are applied at different radii, you should multiply each force by its own distance from the axis of rotation. If it is the same radius case, then of course R can be taken out, as we see in the following cases. Now, before applying it to this idea and that example, let's consider the torque in a different way. The torque tau has a different equation of definition. The torque tau is also defined as follows. Remember the Newton's second law. It is one of the most widely known, one of the few most widely known examples of physics. Maybe E is equal to mc squared is one of them. F equals ma is maybe the second. Alright, so in linear motion again, linear and angular. In the linear motion we had Newton's second law, F is equal to mass times force. If a force is applied to an object, net force, resultant force is applied to an object, of mass m, then that force creates an acceleration on the object. This is very obvious. But what about the corresponding equation here? And we have already seen that mass m in the linear motion corresponds to rotational inertia. So on the right hand side, or we have, instead of m, we should have inertia I. Instead of a linear acceleration, we have angular acceleration alpha, and on the left hand side we have the net force. Now in the case of angular motion, we have the net torque, which we have been talking about today. So torque is also defined by this expression, I times alpha. What about the unit if numbers are given? For instance, the unit of torque is I kilogram meter squared is coming from the first part, rotational inertia. Remember, I is some number multiplied by mr squared, kilogram from the first, meter squared from the second. But also from alpha, we have some radian per second squared. So it's a long set of units. There's no abbreviation for this. Alright, so torque is also, let me write the two definitions together. We have first seen that it is r times f times sine theta, r cross f, so the magnitude is this. And also we see it is I times alpha. Because in some problems, both will be used. Please be careful in solving some problems. If it is not very easy one, if in very easy cases, just one is enough. For example, the problem tells you or gives you the acceleration of the objects such and such, alpha, angular acceleration, what is tall, that's alright. Or, just like these cases, force is given, distance of application is given, and the angle is also given, then what is tall, alright. But in some, a bit more complicated cases, more physical cases, like the ones in physics, which are more suitable to physics 101, which are a bit above the level of high school. So that, in those cases, you should consider both definitions in the solution. So let's try to solve one such problem. Let's unite the Atwood machine that we have been dealing with in the chapter on forces, and also the new concept of torque. Let me write the text of the example and then analyze what we have to do. Two blocks of masses M1 and M2 are attached by a massless and inextensible rope passing over a massless pulley. Not a massless pulley, but a pulley with a mass, as we will see the difference. Massless and inextensible rope passing over a pulley of mass, let's say capital M, radius R, as shown. Write the equations of motion. accelerations, find the accelerations, and C, find the tension or tensions in the ropes. This problem is familiar to us because we have already solved it in chapter 4. The chapter on the forces and Newton's laws. Okay. But there's a slight difference. What was the text in that chapter for this problem? Masses, yes, blocks of different masses are attached by masses and an extensible rope, yes, but it was passing over a massless pulley. So the pulley, this is a disc, but its mass was negligible. Its radius was not important. So that, because we didn't know about the inertia in chapter 4, chapter 3, 4, until chapter 9, when we come to the rotational dynamics, we didn't have anything about the moment of inertia. Because if something is turning, what is happening to the difficulty it shows against the motion? Alright. Now we know how to deal with these inertias. Now its mass and radius are both given. And since it's a disk, let me write it here. It's a disk I pulley, which is a disk is 1/2 m times r squared. But please don't confuse the masses. Little m1, little m2 for the blocks, capital M for the mass of the pulley. Pulley is a kind of disk, and we know the inertia of the disk is 1/2 mr squared. And m and r are both given. Again, let's go back to that problem. How did we solve it? Remember, we said that tensions were the same. So on the two sides, because in that part, let me first draw the picture. In chapter 4, chapter 4 means where we are dealing with the forces only. So this was the case. That is the disk, and these are tension T, tension T. However, now, in chapter 10, now, at this moment, we will first consider them, the tensions, as different tensions. That's one of the main reasons. So this is the tension T1, that's the tension T2. Main difference. Of course, there is the same acceleration. This is wrong, but this is correct. There are two different tensions in this problem. And the two ropes, or in the two sides of the rope, tensions will be different necessarily. If there is no difference, there will be no torque, net torque applied on the pulley disc. So there should be a net torque so that something having a mass and having a radius is now turning around the axis of rotation. So necessarily there should be a net difference in the torque. So T1 and T2 should be different. But now we are not interested in this case. Forget about it. I'll come back to this second picture. Alright, write the equations of course, draw the free body diagram first. For M1, this is the object representing the block. What are the forces acting on M1? Upward force is the tension T1, downward force is the weight M1G. I draw the T1 a bit longer than that because obviously, since M2 seems to be larger, M2 seems to be greater than M1, we expect a clockwise rotation in the system. If the system is turning clockwise, this one is heavier, so that T1 should be greater than M1G. Otherwise, if they are the same, no rotation. If M1 is G greater, it would rotate in the opposite sense. So M1, we can draw this one. For M2, we can draw what? In this case, this is larger, M2G is longer, but this force is T2. T2 is like, yeah, let me also compare them. For instance, T1 is larger than M1G, but T2 is larger than, this amount is larger than, greater than T1. What about the equations? Again for M1, net force, which is T1 minus M1G. T1 minus M1G has to be M1 times acceleration A. A is unknown, T1 is unknown. For the other one, for M2, it is the other way around because M2G is greater, so that it is falling down. M2G minus T2, it has to be M2 times acceleration A. There is just a slight difference because in the case of no inertia, we were writing them as not T1 and T2, but otherwise they are the same. If you T1 and T2, these indices, it was T minus M1G, M1A, M2G minus T, M2A. Here the difference is in the indices, we have different indices, T1 and T2. What about the pulley for capital M? Let me draw the picture for that, and here is the picture. But, for example, we should see here the total picture first. For instance, this is the whole pulley, and those are the objects. For these objects, we said that this is T1, that is T2, and these are M1G and 2G. And that was the isolation of the body from the environment. If you isolate this body, you would write just this one. T1 minus M1G equals that. Similarly, this one. If you isolate, cut it away from the environment, so we have these two forces, and M2G is necessarily greater than that. What about that one? Now, when you look at the pulley, this is the picture you have to consider. What are the forces? This is T1, equal and opposite tensions, and that is T2. So these are the directions. Please be careful. So that T2 will try to rotate it clockwise, T1 will try to rotate it counterclockwise. However, T2 is greater, so that the net result is a clockwise turn for the pulley and for the whole system. That's why we will write the equation. We didn't write it yet. So for M, so there is the same radius, so R and R. So T2 times R minus T1 times R. And that difference is not zero. For M it is tau 2 minus tau 1. What is the right hand side? As we have seen in the second kind of definition, it is I times alpha. I times alpha. I is the inertia for the pulley. Alpha is the angular acceleration. However, these are linear accelerations. And we will also write a relationship between A and alpha. But what is T2? Tau 2 minus tau 1. It is T2 times R minus T1 times R. It is I times alpha. Let me continue here. So we have R times T2 minus T1. What is the right hand side? Inertia. What was it? It was given as 1/2 capital M R squared. Now what about this alpha? And the relationship, remember, between linear and angular velocities, there is no velocity here, but let me just remind you. it was v is equal to omega times I. For the accelerations, we have a linear acceleration is angular times radius. So for angular one, we won't write alpha, but we will write a over r. Which r? Of course, capital R. So we will write here not alpha, but a, which is this a. Okay. So this a. Let me write the a's. This a, that a, unknown but the same acceleration, and this will be the same acceleration divided by the radius of the disk. So as you see, the radii will cancel. So these are one of them, and this one, the other one will cancel. So we have 3 equations now to solve. Now we have 3 equations. What are they? First one, second one, and third one. And it is easy to solve them. Let me rewrite these two. So we have 3 equations. What was it? For first one, T1 minus M1G is M1 times A. Second one was M2G minus T2 is equal to M2A. And the third one was this. What is it? T2 minus T1 after cancellation of the radii. T2 minus T1 is just 1/2 capital MA. 1/2 capital MA. If you add them up, what do we get? Plus T1 minus T1 will cancel. Plus T2 minus T2 will also cancel. So we have A's on one side and weights on the other side. So A multiplied by M1 plus M2 plus half of the disk's mass is equal to M2G minus M1G. M2 minus M1 multiplied by G. So that the acceleration is A is equal to M2 minus M1 divided by sum of them, G is the acceleration of the system. Let me write a comment here. In the other case, in chapter 4, okay, in chapter 4, for instance, we neglected the mass of the pulley so that capital M was 0. There was no such thing as capital M. Capital M was 0. So if you set this capital M to 0 here, it reduces to the expected equation, because remember, or maybe look at the previous notes, you will see that immediately. In such a case where mass of this disk was unimportant, then the acceleration for the whole system would be M2 minus M1 over M1 plus M2 times G. And here, the additional thing is here. If you compare the accelerations, the acceleration in this system is a bit less than the previous one. So this is the acceleration. What about the tensions? It is easy again to put this A in. For example, if you put this A here, you can find T. If you put it there, you can find T2. Let me do it here. Substituting the acceleration in the equations, substituting the acceleration A in equation 1, we get T1. In equation 2, we get T2. Equations 1 and 2 are these two steps. So the result should be will be a bit more complex, but it is not difficult to get the result. For instance, T1 is, let's take M1G to the other side, M1 times G plus A. Since A also contains a G, we can take it out, so that T1 will be M1G multiplied by 1 plus this part. M2 minus M1 over M1 plus M2 plus M over 2. So this is the result for T1. Similarly, for the other one, T2, take it to the other side as positive, but this one to the left as negative. T2 will be M2 G minus A. Take T2 here as positive and M2A to the left as negative, so that it will be M2G also is taken out. 1 minus A. What is A? It is M2 minus M1 over the sum. Let me write a final comment in this problem. Comment. If there is no mass for the pulley, in other words, if the pulley's mass is very negligible, if the pulley's mass is negligible with respect to the masses of the blocks, then we take M to be 0, as I said before, capital M0. If you take capital M0, then please check yourself that T1 and T2 will be equal. Because if you have nothing here and nothing there, although there's a different sign and different index for the first term, you will immediately understand that then T1 and T2 will be identical to T, which we found in chapter 4. Whatever tension we found there, please compare the new one, not once, because in this case we will have only one tension if there is no mass for the pulley. If this is negligible, just this term is dropped, capital M, the others are remaining. This capital M will be neglected so that we have the rest. And if you compare the other remaining terms, they will be equal, and they will also be equal to the previous tension that we saw in chapter 4, where we didn't know about the moment of inertia yet. In the previous lecture, Rotational Dynamics Part 2, we have seen an example where we had a disk around which some rope was wound, and at the end there was a block. And the block was falling from the higher position. And when it falls by a distance h, what is the velocity of the block was the question. And since we didn't know about the torque yet, we solved it by using the energy conservation principle. Now we will try to solve the same problem again, but this time using the concept of the torque, dynamical method in a way, and compare the results. Of course, the results should turn out to be the same, otherwise at least one of them would be wrong. But if you solve the equations correctly, you should necessarily get the same result. So let me remind you the problem again. This is the object. And there was a block. But then it falls a certain height. For example, this is now moving to some velocity v, so that the distance it falls is h. Little mass is little m. Well, now the pulley is mass m, radius r. And maybe you can find it in the previous lecture easily. We applied the energy conservation principle. Let me write the text again. a block of mass m is attached by a rope passing over a disk of mass capital M and radius r. What is the velocity? Of course, linear velocity. What is the linear velocity? V of the block when it falls by a height h. When it falls down by a height h. What's the question? Let me just remind you the previous case. We called the initial and final moments as 1 and 2. For instance, this was 1 and that was 2. And from the energy conservation, we said that energy 1 is energy 2. And if you choose this level to be 0 level for simplicity, because it is easier, maybe, for me it is easier to set the initial value to 0. So it is U1 plus K1 is equal to U2 plus K2. Kinetic and potential sum is again equal to this new sum. So initially, since it starts from rest, it is obvious that it starts from rest, so that there is no kinetic energy at the beginning and no potential because of my choice of y equals 0 there. So it is 0 plus 0. But what is the right hand side? When it passes by this new position, which is down the first one, lower than the first one, so this is at the height minus h with respect to the initial 0 level. So initial potential is simply minus little m, don't confuse the masses by the way, little m is the mass of the falling block, mass g and h, and it is negative. Plus there are two kinetic energy terms, one for the block, one for the rotating disk. So there are two terms, plus 1/2 little m v squared plus 1/2 capital I omega squared. This is for the block, this is for the rotating disk. And at the end we obtain some relationship. It's easy to get it. Anyway, because omega and v are also related, because v is the velocity, this block is moving at velocity v. But any other point along the inextensible rope, which has the fixed length, this point is moving at the same speed. This point is moving at the same speed. This point, any point on the rim of the disk is also moving with the velocity v. And this is turning by some angular speed omega, and we have a relationship, remember, v is equal to omega times I. So that 1/2 little m v squared plus 1/2, another 1/2 for the inertia, mr squared v squared over r squared, so that these r squares will cancel, and v squared over 2 multiplied by little m from the first term plus capital M over 2 from the second equals mgh. And indeed, v turns out to be root 2mgh divided by this parenthesis. And this was the result. Now this result we obtained by the energy principle. Now we will solve the same problem using the torques dynamical method. Now let us solve it by the dynamical method, which means using the torques and accelerations and kinematical equations by the dynamical method. little means the following. You should consider the forces, torques, etc. In this case, we have the object disk to turn. And there is a tension T. Let me warn you, this tension T is not equal to mass mg. It would be a mistake if you do it. If you assume that T and mg are equal, this is a mistake. You should write the equation for the little block and then write another equation for the turning disk. So that for little m, what can we write? This is just simple free body diagram as before. That this is the weight little mg and that's the tension T. And they are not equal. For little m, we can write mg minus T is equal to m times a, as before. But for capital M, what can we write? It is the torque applied. And that torque is, this is the distance radius, and that's the torque, they are at right angles, so sine 90 is 1. Torque equals I times alpha. What is the torque using the other definition? Torque is radius r multiplied by the tension. It is not, be careful, it is not radius r times mg. It is wrong. R times T, because tension T is the force applied on the rotating disk, mg isn't. And T and mg are different also. Be careful. T and mg are different values. They are related through by the acceleration. So R times T is the torque on the left hand side. I, since it's a this 1/2 mr squared is given by the problems. 1/2 capital M R squared, and don't forget to write alpha as A over R, as we did in the previous case. So that these are being cancelled and we find T as capital MA over 2. And once you put this T here, you get the acceleration. So that after plugging this T in the previous equation, we have mg minus T, but we don't write T, we write MA over 2. And A over 2 is equal to little MA. So group the A terms. Acceleration multiplied by sum of them, little m plus capital M over 2. On the other side we have little mg. I keep it on the board to compare the result for the velocity. Alright, what is the acceleration now? Acceleration turns out to be, take it to the other side, m over, little m over that parentheses, little m plus capital M over 2 multiplied by g. So this is the acceleration. Whose acceleration is it? It is the acceleration of the falling block. This block has an acceleration a, and that one is turning at an angular acceleration alpha. It's getting faster and faster. Okay, how do we use this A in finding the velocity of the block at a certain later instant? Then, once it falls to a height h, we can go back to chapter 2. Kinematical equation, it's a linear motion. Now, it's a linear motion for the block, because the block is not turning, the block is falling along a vertical line. So that we can use v squared is equal to v0 squared plus twice acceleration and height h for the block. What is the initial velocity? 0. It starts from rest. So v squared, or v is equal to root 2 times acceleration, which is this thing, acceleration mg divided by m plus m over 2 multiplied by h, and if you compare these, they look the same. So that we can find the same value by using different ways. Maybe by the energy method, conservation of energy principle will be used. Maybe by using the dynamical method, linear angular accelerations. And one of the important things here, don't forget please, this conversion A is equal to alpha times R, maybe little r, maybe capital R, of the rotating radius of the rotating object, which is in this case the disc, the pulley. Now let's have a similar example, but before that let me compare a certain, let's have a short comparison. For example, if we have a reel like this, a rope is wound around a certain cylinder. Yeah, let's say a very thin rope. It is wound around the cylinder and we leave it and it will fall down by unwinding. And at the same time I will set free another point object which is not rotating. So we will compare the linear motion of the falling lid with the angular motion of the falling wheel or reel cylinder. Which one do we expect to reach the ground first? Yeah, they will start from the same height with the same zero initial speed, but do they reach the ground simultaneously? No. Which one will win the race? We will see. And maybe let's compare it. You just hear the voices. So let's compare and start leading them at the same moment. 3, 2, 1, 0. As you might expect, the lid has arrived before the wheel. Let's now understand it on the board. Now, in the new example, we will have something falling down, getting faster, and also unwinding. A rope is wound on a wheel and is set free at a certain height. Find the velocity v of the wheel after falling by h. Again, we will compare the two methods, energy and dynamical weights. This time it is not the block which is falling down, it is the disc or pulley or wheel, reel, some cylindrical object around which a rope is wound. Now using the energy method, for instance. 1. Using the energy conservation principle. Again, let's compare the two moments. 1 is the initial one, 2 is the one after having fallen by a height h from the initial reference position. Alright, so E1 is E2. So E1, the energy, is equal to energy E2. And obviously, potential plus kinetic is plus kinetic again. But for simplicity, we choose this initial speed as 0 and the initial level to be 0 level, so the initial it has neither a kinetic nor a potential energy. So it is 0 plus 0. But when it falls and it passes by, it is still moving. When it passes by this height h from the initial one, it has a negative potential energy, M, G and H on the one hand, plus two kinds of kinetic energy. One is the kinetic energy, this is capital M by the way. Let's say the radius is R. Radius is R. So radius is R, mass is capital M. So they are given. And also, we have learned anyway, but let me rewrite it. I is 1/2 mr squared for a disk, for a cylinder. Alright, let's use the same given letter. Capital MGH, 1/2 capital M V squared. V is the velocity of the center of mass, and omega is the speed around the center of mass. So it has two kinds of kinetic energy as before. Then it will be 1/2 I omega squared. So this is the potential, and these are the kinetic energy terms. But as you see, there are too many letters, capital M, capital I, omega, V. However, they are related because I is anyway m times 1/2 mr squared. And V and omega are also, as you will see, related by omega times R equals linear speed V. So now go one step further. Take it to the other side. 1/2 multiplied by capital M V squared plus I, but I is also 1/2 capital M R squared. Omega squared is V squared over R squared. Together we have MGH on the other side. So M's cancel first of all because there is only one kind of mass, unlike the previous one. And also these R squares will cancel. So we have V squared multiplied by V squared over 2 multiplied by 1 plus 1/2 equals GH. So it is 3/2. So V squared over 2 times 3/2, 3 over 4. So we understand that V turns out to be square root of, this is 3 over 4, because inside we have 3/2, 3 over 4. So 4 over 3, so 4 over 3 GH. So velocity is found by this energy conservation principle. Now let's find it by the dynamical way when we use the torques. In this case, using the dynamical way, so this is the object which is unwinding while followed. What are the forces on it? There is the weight, capital Mg, and tension T in the rope. There are two opposite but not equal forces. If they were equal, then it would either stay at rest or fall down at constant speed. However, it is getting faster and faster. It had zero speed at the beginning, now it has obtained such a velocity when it falls by h. Alright, so they are not equal. What is the force equation for this object? For the linear motion of the center of mass, and G minus T is equal to M times A, as before, just like in the third chapter, fourth chapter, fourth and fifth, the Newton's laws. This is for the linear. For the rotational motion, we should write one more equation. For the rotational case, we have tau is equal to I times alpha. But what does tau equal to? It is just the tension which rotates it, not the weight mg. Mg, the weight, does not rotate the object because it passes by the center of mass. Otherwise, any object would start to turn clockwise or counterclockwise by itself without any torque. If there is a weight, of course, that weight is applied by the center of mass. So there is no R. R cross F. Remember the definition of torque. R times F times sine theta. There is no R. Because F, such as mg, is applied just at the center of mass. This is the meaning of, anyway, that's why the meaning of center of mass is the point at which the weight is applied. So that there is no R. mg does not rotate the object. It is only the tension T in the rope which is applied at another point. And this distance is R. So it is only torque. It is only tension T. It is only tension T that rotates it. So torque is simply radius R times the tension. Tension is still unknown, but it is the force that turns the object, in this case, clockwise. Not the weight, please be careful. It is not mg times R, it is T times R, and T and mg are different. So torque is RT. And also here we write, using the second equation, new form of this is, what is torque? It is R times T. What is I? 1/2 mr squared. 1/2 mr squared. What is alpha? Alpha is A over R. Again we cancel the R's altogether. These R's will cancel. So tension turns out to be half of the MA. 1/2 M times A. And if you put this T, if you substitute it in the first equation, you can get the acceleration. Let me again keep it on the board to compare the results. Alright, then the acceleration turns out to be, rewriting equation 1 here, mg minus tension T, but instead of T I write ma over 2 minus ma over 2 is equal to ma. So m's are the same, so they cancel from each term. Take a over 2 to the other side, we have a plus a over 2 is equal to g. So this is just 3a over 2 is equal to g. So a comes out to be 2g over 3. So it is, that's why in the previous race, it is the lid that has won the race. The rotating object does not have the acceleration g. The other object, remember we compared these two. Objects. One was a directly falling lid of the pen, the other was unwinding real disc. It is the lid that won the race. It is obvious that because the acceleration, linear acceleration of the rotating, unwinding disc is just 2/3 A. It is less than A, it is not A. A of the lid is G, A of the real whale is 2/3 G. That's why the lid, freely falling lid, had a greater acceleration than the other one. That's why it is the lid, falling object, without any rotation. Alright, now let's find velocity. Again from the previous equation, from v squared is equal to v0 squared plus 2 times a times h, not ga. So that v turned out to be, this is just 0. It is just 2 times, acceleration is 2/3 g and h, so it is 4 over 3 gh. As we compare, they are the same. So that v is equal to just 4/3 gh. So these two results, as you see, of course are the same. And again we explained why it is the object falling directly down without any rotation. Because it has converted all the potential energy to the only one thing, which is the linear kinetic energy. However, the rotating object has to allocate the initial value to two parts. One for the falling part, linear kinetic energy of the center of mass, also it has to allocate some of the resources, resource means in this case the initial potential energy, to the rotational part. The sum of the energies, sums are equal, but just if you compare only the linear speeds, it is the object which is falling directly, which has greater linear speed, of course. In some cases, we have some rolling objects along an inclined plane. For instance, we have a cylinder or a wheel, for example. This is angle theta, and this object has mass m, radius r. Find the acceleration a of a disk moving on an inclined plane of angle theta, of a disk of mass m, radius r, moving on an inclined plane angle theta. And there is a friction on the board between the plane and there is some friction on the plane, or between the friction between the disk and the plane. There is some friction, but the coefficient is not given, so it means we don't need it. Alright, let's now take into account also the concept of friction, otherwise it wouldn't turn. There is a friction, that's why it is rolling. We will see soon the rolling motion as well, but now we can solve it by the equipment we have, the equations, the formulas, the ideas, physical ideas. Alright, now let's draw the free body diagram, because this is the object. What are the forces acting on it? One is the weight mg. The other is the friction acting between the plane and the disk wheel. So this is the force little f. And remember also from the previous chapters that mg has to be decomposed into two parts, horizontal part, parallel part and perpendicular part. So this is angle theta. Therefore this mg has two components. One is this one, the other is that one. Since this is angle theta, the parallel component is capital Mg sine theta, perpendicular one is capital Mg cosine theta. And this friction is, maybe you can write it as normal force times coefficient, but anyway, it is enough to write it as F. It will anyway cancel. Alright, first consider the forces without the torque, and then the torques. For the forces acting on the object, for the forces acting on it, the net force is mg sine theta downward minus f upward, and they are not the same, so mg sine theta is a bit greater. So it is mg sine theta minus the friction is equal to m times a. F is unknown, a is unknown. And for the torques, rotating it, as we have said previously, we have learned that this mg mg sine theta, mg cos theta. This force cannot rotate the object, cannot turn it. It is only the friction force between the plane and the disc that rotates it clockwise as it falls down, slides down. Alright, for the torques, tau is equal to I times alpha. What is the torque? Tau is equal to this radius, which is r given, and r times f. R times f. It is never r times mg, be careful. R times f. Alright, then I, what is I? I is equal to 1/2 mr squared. Is it turning around the center of mass? Yes, it is. It is. If you focus on the rotating object, the disk, it is turning around the center of mass, and some external force, friction force, is applied on it. So we don't need the parallel axis theorem in this case. It is just this I. So that tau is equal to I. Tau is r times f. I is 1/2 mr squared, capital M, capital R squared, and alpha, which is over R again. So that these r's again will cancel. F is already found in terms of M and A, as it is MA over 2. And then you put this F in the previous equation and get the acceleration. Mg sine theta, first term, minus F, but in terms of F, I write as MA over 2 is equal to MA. M's cancel, so that it is 3 over 2a, if you take it to the other side. It is g times sine theta. Acceleration will be 2/3 g sine theta. Remember that if it were not a rotating object, but just a block, if it were just a block, remember that acceleration would be just g sine theta. So if you compare them, this is again a bit less linear acceleration multiplied by 2/3. 2/3 is less than 1. So this is just 1 g sine theta, this is 2/3 g sine theta. Of course, in this case, again, if you leave the two objects simultaneously on the board, assuming that block is falling in spite of the friction, etc., again, it will be the acceleration, since this is greater, it will be, but this is for the frictionless case, remember. This is for the case of frictionless plane. Be careful. If there is friction, also you should compare using the coefficient of friction. For the frictionless inclined plane, the block has an acceleration g sine theta. In this case, the acceleration, linear acceleration of the center of mass, A, is just 2/3 g sine theta.